Hello and welcome to MT3. We have now left series solutions to differential equations, and now we are on to another topic which may not look like it's related to differential equations, but it is going to be when we start doing Green's functions. The concept I'd like to introduce today is the Dirac delta function, which is given as delta, written as delta. This is lowercase delta of x minus x naught. This is a very peculiar function. In fact, it's not even a function. And it's described in Riley, Hobson and Benz 13.1.3 and Arfkin, Weber and Harris 1.11. Now I find the treatment in Arfkin much better than the one in Riley's book, so please look at Arfkin's book if you'd like to find out more about the Dirac delta function. Of course, as always, if you look online, you'll find a wealth of information there, so feel free to search Google. So here's the definition of what the Dirac delta function does. If you got an integral from x1 to x2 of some function f of x times the Dirac delta function, Dirac delta, let's drop the function if I can remember it, of x minus a, so now x naught is a, integrated over all x in this range. Now this is defined to be f of a if a is in x1, in the range x1 to x2, and it's 0 otherwise. All right. Now think about this for a while before you go forward. So if the point A is in this range, that means if the point A is in this integration range, then we will get f of a. That means this Dirac delta is collapsing f onto one value only, f of a. And if a is not in this range, then it gives you nothing. This is suspiciously close to what the Kronecker delta did, isn't it? The Kronecker delta of ij, it set I is equal to j, and it would give you a 1 if I is equal to j, and a 0 otherwise. This is in fact the function space equivalent of the Kronecker delta. So this Dirac delta is the function space equivalent of that. It picks a point A in your function space, and if A is included in the range of integration, then the function f is, the result of this integration is simply f of a, otherwise 0. All right. So more commonly we use this form of the Dirac delta. We have an integral from minus infinity to infinity, which means all the x-axis. In which case a is bound to be in this range, so this is simply, so this kind of case-wise equation becomes simple. It's just that the integral of minus infinity to infinity of f of x times the Dirac delta of x minus a is simply f of a. Yep. Now if f is equal to 1, what this means then is that the integral of minus infinity to infinity of the Dirac delta is 1. So it's a function which has a unit area under it. So it's an interesting function. It has unit area under it. Now while we are here, let's just, do some experiments here. I'm going to draw a bar, and let's ask ourselves simple questions. What happens if I integrate this Dirac delta from a minus some epsilon, I don't know, it's epsilon is positive, but it's a small positive number, to a plus epsilon, and I want to put a Dirac delta in there? What will this be? Well, the question we need to ask is a in this range? So is a in a minus epsilon to a plus epsilon? Oops. And the answer is yes, it is. So this thing then will be 1. And you can make epsilon as small as you want, and you will still get a 1. So this thing is a very peculiar function. You can integrate around a as, so this is the x-axis, this is point A, let's use a different color here, then I can integrate as close to a as I want, and I will get a 1 from the Dirac delta. Or I can integrate as far away from a as I want, and I will still get a 1. It's as if this Dirac delta is concentrated here. It's spiked over here, and it's nowhere else. Why do I know it's nowhere else? Because if I decided to integrate from a minus epsilon to, let's say, if I decided to integrate from, actually, let's keep that where it was. And let's write another thing down here. So if I decided to integrate from, let's see, a minus 2 epsilon to a, that's not what I want, yeah, a minus 2 epsilon to a minus epsilon of delta x minus a dx. What is this equal to? Well, is a in the range a minus 2 epsilon to a minus epsilon? That's what we need to ask. And the answer is no. So this is 0. Now what this means then is that if I draw the same kind of figure here, this is my x-axis, then we have the point A, and now using green, I'm now integrating from a minus 2 epsilon to a minus epsilon. Now as epsilon goes to 0, these 2 points start to approach a, but they never include a. They can get very, very close to a, and I will still get a 0. And you can do the same for a plus epsilon and a plus 2 epsilon. You will still exclude a and you will get a 0. Everything, this Dirac delta is concentrated at a and only at a. Okay, so that's our little analysis of what this thing looks like. So here's what we have concluded then. This Dirac delta is concentrated at a. It's infinitely thin. It's infinitely peaked. Its area is 1, since the integral from minus infinity to infinity of the Dirac delta is 1. And this is what I've just shown you. Yeah, we can look at this infinite integral as the limit epsilon tends to 0, where we integrate only around a and we'll still get 1. So what kind of function is it? In what sense is this a function at all? We haven't seen any function which behaves like this. Well, here's one way of looking at it. Let's define a delta n. This is not the Dirac delta, but it looks like it. A delta n of x minus a. Here's a. And delta n is defined to be this square, this rectangular thing. So when it's 0 if x is less than or equal to a minus 1 over 2n. So it's 0 that side, it's 0 on this side. And when in between, so in between these two limits of a minus 1 over 2n and a plus 1 over 2n, this function is equal to n. Now you can see that this function has an area of 1. Why? It's got a height of n, and it's got a width of 1 over n. So the area is n times 1 over n. So let's put an n here. N times 1 over n, and that's 1. Now here's the interesting thing. As I change n, as n goes to infinity, n gets larger and larger, this width will get smaller and smaller, but the height will get larger and larger. And because of this construction, the area will always remain 1. So here's what's going to happen. As n gets larger, this kind of flat squattish thing will become narrower and taller, even narrower and taller, such that its area always remains 1. And in the limit n goes to infinity, it's concentrated only at a. It's 0 everywhere else, but its area is still 1. So in that limit n goes to infinity, this well-behaved function delta n of x minus a becomes our notorious Dirac delta. And there are other ways of doing this kind of construction of the Dirac delta. It's not, there are an infinite number of ways. See, this function here, this box function, is not differentiable. That's kind of bad. Mathematically, sometimes you want to see something that's differentiable. So these examples are differentiable. What we can do is we can use a Gaussian. So this is, now we define delta n to be n times e to the minus n squared times x minus a squared, and it's divided by root pi. So it's a normalized Gaussian, and this is what it looks like. If I drew an axis, this is my x-axis, this is a, then this function is a Gaussian centered at a. And as n gets larger and larger, it gets more and more peaked, but also much taller. So in the end, it becomes a Dirac delta. This is another way of writing down a Dirac delta. And finally, this one, which is quite important because it relates to Fourier expansions. Here we write a Dirac delta in terms of sine of n times x minus a divided by pi of x minus a. Now you can see that as x tends to a, this looks like it's not well behaved, but it is, because you take you use L'Hopital's rule for your limits, and this is well behaved, has well behaved limit. But as n tends to infinity, this will also get more and more peaked, and in fact it looks like this. For any finite n, this function looks like this. It's peaked like that one, but it has oscillations. And as n gets larger and larger, this thing gets more and more peaked, and the oscillations get more and more cramped next to it until it becomes a nice spike, and that's your Dirac delta. So these are all examples of the Dirac delta. You can look at the Dirac delta as a limit of each of these understandable normal functions. Here are some properties which we're going to prove now. The first is that it is an even function. Now it should have been obvious it's an even function, but let's prove it. So I put functions in quotations here because it's not really a function. So delta of x is equal to delta of minus x. It's even. Then if you scale x, so delta of a times x is equal to 1 over modulus of a times delta of x. And the third is that x times delta of x is 0. So how do we prove these? Now pay attention to the ideas here, because these are common to any proof involving the Dirac delta. So if you want to prove that delta of x is equal to delta of minus x, let's start with the thing we want to simplify as delta of x. Put it under the integral. So we have the integral minus infinity to infinity of f of x times delta of minus x dx. Now I don't know what to do with delta of minus x, but I know what to do with delta of x. So change variables. Let x prime equal to minus x, so dx prime is equal to minus dx, and this means you get minus the integral of infinity to minus infinity f of minus x prime delta of x prime dx prime. Now that's good. Well, first of all, we can get rid of that minus sign by switching the integral limits from minus infinity to infinity as we had it before. So that's here. And now we know what to do with the delta of x prime, but delta of x prime, this is simply delta of x prime minus a, where a is 0, right? It's centered about 0. So we will get f of minus x prime, where x prime is 0. So this is equal to f of minus 0, which is f of 0. But f of 0, by definition of the delta function, is the integral from minus infinity to infinity of f of x delta x dx. Now we compare this last term with the first one, and it looks the same. Here we have a delta of minus x, there we have a delta of x, so we make the identification delta of minus x is equal to the delta of x. That's the first result. Let's now prove the second result. Same way. We first make a choice, we let a be greater than 0. So we're going to use this. And now we start off again with what do we want to show? We want to show that delta of ax is equal to 1 over modulus of a delta of x. Let's start with delta of ax. So the integral from minus infinity to infinity of f of x delta of ax dx. Well, how do we handle that? I don't know how to handle this. So let's change variables to x prime again, where x prime is equal to a times x. Dx prime is equal to a times dx. Because a is a positive constant, nothing changes with these limits. So we have minus infinity to infinity, f of x prime divided by a, delta of x prime, and then we have dx prime divided by a. Well, that's easy to handle because delta of x prime simply collapses this integral to f of x prime over a, to f of 0, sorry. And then we have the 1 over a. So we have a 1 over a times f of 0. But f of 0, by definition, is the integral minus infinity to infinity of f of x times delta x dx. So we can bring the 1 over a in as the integral of minus infinity to infinity f of x in square brackets 1 over a delta x dx. And now we make the identification with these two terms circled in red. And we must have delta of ax is equal to 1 over a delta of x for a greater than 0. Now for a less than 0, here's what we can do. We consider the integral of from minus infinity to infinity of f of x times delta of minus modulus of ax. So I have, because a is less than 0, it's a negative number, so I take the modulus and I add a minus sign to remind me that this is a negative term. And now we do a change of variables. We could do a change of variables. So let x prime is equal to minus modulus of ax and use the same proof as we had above to show that this is what you get. Or, I've given a hint here, you could use the second of the results. So I'm going to leave that to you. Show that we get this. And in general, delta of ax is equal to 1 over the modulus of a delta of x, where the modulus of a is greater than 0. That's the only condition. Because if a is equal to 0, we'll have delta of 0 there. That's why. So we must have a to be non-zero. Okay. Now this delta function is related to another kind of function called the Heaviside step function. And this is a function which is used a lot in engineering and also in physics when you introduce perturbations in quantum mechanics. You'll often say at time t is equal to 0, the perturbation is switched on. So it goes from 0 to 1. 1 is the full value. So here we have the Heaviside step function, h of t is defined. I put t here because it's often defined as a function of time, although there's no need for thinking of t as a time. It's anything. So we have some variable t, independent variable t. At t is equal to 0, ht gets switched on and it takes the value 1. Before that, it's 0. So ht is 1 for t greater than 0. It's 0 before that. Now, what we're going to show is that the derivative of the Heaviside step function is the delta function. Now, this should be, if you're starting to develop an intuitive understanding of the delta function, of the Dirac delta, you should see that this is quite plausibly the case. And one way to see it is not to look at ht, because ht can't be differentiated. But what you can think of is think of ht itself as a kind of limiting case of a set of functions. So if I have t here, 0 here, I should have drawn another line. Let's draw it. Yeah. And now if I take a series of functions which look like this. Here's the first. Then the second. Sorry, this is really badly drawn. They should all, let me draw that again. And I'm going to label one more thing before I do this. This is a half. Okay, so now let's draw the first one again. And here's what I need to do. Has to go through the half. That's the first one. Then the second one. More steeped. And you know, if you regard h as the limiting case where these smooth functions become more and more like a step function, then you can start to differentiate these functions. And if you differentiate these, you'll find you end up with a spike. And that's your Dirac delta. So this is a nice exercise where you can actually show that this gives you the Heaviside step function in this limit where these become infinitely sharply, they change infinitely sharply. Right, let's go on. So how do we prove this without going through that graphical proof? Well, simple. Integration by parts. Let's start with the integral from minus infinity to infinity of f of t, h prime of t dt. And now for what I'm going to do, I'm using infinite limits is going to be bad, so I'm going to take the limit m goes to infinity. This is simply the limit m goes to infinity of the integral minus m to m of the same thing. All right, now I can handle this. So this is the limit m goes to infinity on the outside. We'll just forget about it for now. Curly brackets. This is of the form, there's a derivative here, so what we can do is use integration by parts. So we have f of t times h of t from minus m to m minus the integral from minus m to m of f prime of t h of t dt, close curly brackets. These boundary terms are simply f of m h of m minus f of minus m h of minus m. But guess what? H of minus m is 0 and h of m is 1 because m is positive here. So this simplifies our boundary terms, and then we have this integral here can be written as minus the integral from 0 to m, because when t is minus at any negative value, h of t is 0. The only non-zero h of t is when t is positive, 0 or is larger than 0. So we can take the integral from 0 to m of f prime of t, and then in that case h of t is 1. So I can put a 1 there. Okay. And the integral of a derivative of a function is simply the function. So what we end up with then is the limit m tends to infinity, curly brackets, f of m, that's from here. And then we have f of t from 0 to m, which is, you put it down here, and what you're left with is just f naught. Lovely, isn't it? But f naught, by definition, is the integral from f of t delta t dt. And now you compare this integral with the first one we began with, and what you get is h prime of t is equal to delta of t. Nice. Okay, so that's the link between the Dirac delta and the Heaviside step function. And as I said, you could see this geometrically if you look at it as the Heaviside step function as a limiting case of a series of gradually steeper and steeper steps. If you think you've understood what's going on for the Dirac delta, then please try your hand at proving these. This is discussed in Riley, Hobson and Benz and in African Weber Harris. The Dirac delta of a function g of x, where g of x has roots at points ai and there are no degeneracies. This is very important. The Dirac delta of that is given as the sum over the roots, the Dirac delta of x minus ai divided by the modulus of g prime of ai. Now this might look like, oh my god, how the heck can I prove that? So have a look at Arfkin's book or Riley's book where they explain how you can start to prove this, and it's quite nice. The other thing which I think you can prove using integration by parts and the techniques we've seen above is that the integral from minus infinity to infinity of f of x delta prime of x minus x naught is minus f prime of x naught. This is something which I think you should be able to try without looking anywhere. But this one you might need some hints from these books. But who knows, maybe you'll get it, yeah? I put a note down here saying that, if you're uncomfortable with the idea of the Dirac delta, think of it as this, always think of it as this limiting case where you take the limit n tends to infinity of one of these well-behaved functions you've seen above. And in that case, the integral of any function times the Dirac delta is the limit n tends to infinity of the integral of the function times these well-behaved functions. Now, I find that sometimes this approach is more helpful in visualizing what is happening, so I can then visualize that as this function gets more and more tightly peaked, then this integral collapses to just this function evaluated at one point, and this can be useful at times. All right, so here's our kind of overview, and not just an overview, but also some very nice properties of the Dirac delta. Uh, it's the object which we're going to use when we start to solve differential equations using the method of Green's functions. And there it's related to the idea of an impulse. And what is an impulse? It's when you hit something abruptly and sharply. You have a force which is transmitted in a very, very short time. And that is described by a Dirac delta. So we'll see how this concept is used for solving differential equations soon. Thanks for watching.